So this week we're going to do work energy theorem, and then again next week we're not going to have any meetings. Um, so because it's the Thanksgiving week and all that. So we only have two more labs after this one, and it's simple pendulum and Archimedes principle, and um, we'll see. Archimedes principle is a neat concept, but it's not a really good lab, especially remote. It doesn't really make us much sense. So we'll see if we can even get to that one. But I never did a quiz thing. Um, Kind of had plans to, never did, where this whole thing works out. So I'm going to probably do like a little final quiz thing for everybody, but it's going to be something that's not going to be like a final for the class. It's not that insane of an intensive class. So what I'm probably going to do is just like um, assign like a final quiz that's just like several problems of some concepts that I think are the most important, and then of course I'm gonna post a practice quiz with full solutions, and then the quiz itself will have very very similar problems, almost identical. So it's gonna be basically a given, but I'm just gonna have you guys do something else. Okay, that's all it is. So don't trip out about it too much. Like everything else in this course, we can grade it pretty easily. Anyway, and of course you can email me questions about that if you have any, but look for that later this week. But anyway, so lab 9, work energy theorem. Um, Essentially, so work energy theorem is the concept that basically says that the work that you do on an object can equal the total energy that object has. Let's say if it started with zero energy, like some object sitting at rest on some, let's just say, frictionless surface, and um, hmm, no, it isn't. I see. There's a message. Everybody thought it was me, but it's not. Okay, good. So we have an object sitting at rest here. Let's just say, and we start pulling on it with some force. And let's say we pull on it over some distance d, right? Well, or I can even just say, to make it even a little more rigorous with calculus, we say that we have some starting position x naught. Let's just say. So let's call this x naught, and then it comes to some final position over here, and we stop pulling on it at this point. Let's just say. We don't really have to stop pulling up. Let's just say we stop pulling up for simplicity. It's going to have some velocity over here. It's going to have some final velocity at some final position, right? Now the thing is, this thing had no energy, to start with, and now it has kinetic, right? So where'd that come from? Well, essentially it came from me doing work on this object. And it came from me applying this force to it. That force was accelerating it, and accelerating it gives it some energy, right? Because you're giving it some velocity, and then when you have velocity, you have 1/2 mv squared. You have kinetic energy, which means you have energy, right? So where'd that come from? And the answer is it came from the work that I did. It came from the force that I applied. The way that we represent this is that the work done is typically, it's, to be completely rigorous, it's the force vector dotted with the distance vector. Now that just really means that you need to have the force and the distance being in the same direction. If they're not in the same direction, then it doesn't actually count as work being done. So um, the fact that gravity is pulling down on this thing, but it's not actually moving down because it's stuck on the track, means that gravity is doing no work on this object, even though it is applying a force, right? If I push against the wall, I'm applying a force to that object over a certain amount of time, but I'm not actually moving it. It's not accelerating it. Therefore, I'm not actually doing any work to it. It's not gaining energy from my having pushing it. The thing is that we're going to write this as, so the dot product here will be cosine of theta is another way to write this, where theta is the angle between the two vectors. Angle between f and x. Another way you'll often see it written is really for, this is generally speaking, this is for a constant force over a set distance. But of course, in calculus, or in physics, in the real world, and also in your calculus class, often we don't deal with things that are just constant over an entire region. So the way we handle this is we actually say it's the integral from some starting position to some final position of f dot dx. Okay, now the dot there takes care of directional component. Now, for us, we don't really care about, because we're going to make our force and direction distance in the same direction, right? So we don't have to worry about the dot product. I'm just kind of mentioning that to you because that's literally what's happening. But this is kind of the form that we're really going to think about. It's the integral of your force dx, okay? That's really just, multiplying your force and your distance. But because it's the integral of your force dx, there's another side piece of information here. If you have a force versus distance plot, whatever line you have, let's say this is a non-constant force that's increasing linearly with time, and it stops right there. Well, the integral is your area under the curve, right? So if you take the integral of this thing, you'll get this area under here, and this area actually turns out to be the work. Okay, and that's just another concept is, relating straight to the fact that that's an integration, and integrals area under the curve. So it turns out, and also if you look at this thing just by units of area, you can see that if you take this triangle here, it's, your 1/2 base times height. Well, your base is in units of, the width of your base is in units of meters, and your height is in units of force, or newtons. So therefore you have newtons times meters, which is force times distance, which is going to be joules. Okay, joules again are the units of energy. Okay. In our lab today, we actually deal with, one of them is this situation here. We have this linear force, non-constant linear force, which actually going to be exerted by a spring. And the other one is going to be a constant force exerted by a weight hanging over the edge. And the lab's uploaded if you guys want to see it. So I'll do the derivation for you really quick. Good reminder of some Newton's second law stuff and some force diagram stuff, which can get hairy if you don't think about it too often. So I'm going to call this little mass down here mass hanger. I'm going to call this mass over here mass cart. There's a force pulling this cart down. I'll call that F hanger. That's the weight of the hanger. But the system isn't going to accelerate at G, right? Because there's some resistance here. And actually this mass down here isn't going to accelerate at G down because there's some tension pulling it up, right? That same tension is acting on this cart up here. And this derivation is also in the lab handout too. I think that they do something almost identical. I think actually they added an appendix that makes this more clear or something. But either way, so reminder of some stuff here. Just draw your force diagrams, right? What forces are acting on this cart up here that we actually care about? Yeah, there's gravity acting on it, but we're going to assume a frictionless track. So the tension's pulling it forward. Down here in this mass that's hanging, we have tension pulling up and we have force pulling down. That gives us two equations, right? One thing we know is that the system accelerates at A. Okay, that goes for the mass of the cart and the hanger mass that both accelerate at A. So that allows us to solve the system, because what we can say is we have two different equations here. We have one for the cart. We have that the tension of the cart is going to equal the mass of the cart times the acceleration of the cart, F equals ma, right? And down over here we have the force of the hanger minus the tension, because they're opposing each other, is going to equal the final mass of the hanger times the acceleration of the hanger, right? So those two equations there allow us to solve for tension, because on this left side equation here, I can go ahead and divide out the mass 1, so I get tension over mass 1 is equal to, or not mass 1, is supposed to be mass cart. Okay. Mass cart is equal to A, so tension over mass cart is equal to A. I can substitute that directly into this equation over here, and again, I should mention at least, I mean, the force of the hanger is actually going to be the mass of the hanger times G, right? That's going to be the weight of the hanger. That's what FH is supposed to be. So I can actually write that as mhg, so mass of the hanger times G, minus T is equal to mass of the hanger times A, but A is actually T over mc. And now I can solve this thing for T. Now the way I do that is add the T over to the other side with the other stuff that has T. So mhg is equal to mh over mc times T plus T. I can factor the T out. So I'll have mh over MC plus 1 on that side. Go ahead and do some common denominators there, because we don't like seeing summations of fractions. We like seeing one big fraction. So the 1 is actually MC over MC. So this would be MH plus MC all over MC. And then I would multiply it over to the other side. So then I would get MH, well, let's go ahead and write it in 2 steps at least. I'd get MC over MH plus MC times MHG is equal to T. Okay? And that would be my expression for T right there. Now, the reason I want T is because in this lab, we're actually trying to figure out, we're gonna accelerate that block up here, this cart. We're gonna accelerate it with that force T, and we're going to take a speed measurement right at the end, right before it hits the end here. We're gonna take a speed measurement. So right here, there's gonna be some final velocity. And what we're gonna do is we're gonna calculate the work done, and we're going to compare that to the final energy of the system using the final velocity, because it's going to have kinetic energy. We're going to take the velocity squared times mass times 1/2. That'll give us the final energy of the system. And we'll see if our work was equal to that. And then therefore we're testing the work energy theorem, right? So there you go. There's the whole thing in a nutshell. Now, the way to calculate work here is we have some distance that we travel, delta x, our displacement, and our work is going to be the force applied multiplied by the distance. In this case, the force applied is T, and then our distance is delta x. So the work is going to be this MC, I'll put the MH up there on top, over MH plus MC times G times delta x. That's going to be our work. So for the first part, we have the constant force, part A or whatever. They ask you to calculate the work done on the cart. This is what you're going to use. You're going to use that expression right there, using the masses and knowing G and knowing what the displacement is. They also give you an average force applied, which you can just use that and multiply by the distance, but I feel like that's in there by accident. They didn't mean for you to keep that in there or something. I don't know. But use this one because you're going to get the correct value, and the value that I'm looking for if you use this expression here. So this is what you're going to use for part A, or the analysis for part A, or whatever it is. For the next part, we have a cart being accelerated by a spring. Right, so right here we have the force being applied on this cart, which is going to be equal to negative kx, right? And well, we can kind of, well, let's drop the negative for now, just because the negative really just means the restoring force, and the negative refers to your equilibrium position being x equals 0. Here I'm not really worried about making my equilibrium position x equals 0. So the force magnitude, let's just say, is kx. I just kind of spewed out some stuff there, but really what that means is, the reason it's negative kx is because x is your equilibrium position. So when you spring back towards 0, or in the negative x direction, you plug a negative x into negative kx, and you get a positive force, which means you're pushing you back to the right. And if you have a positive x, which means you're past the equilibrium position over here, then you plug that into negative kx, you get a negative answer, which means the force is pushing you back to the left. So it's always a restoring force, hence the negative. Now, here, all I really care about is the magnitude of it. So I'm just going to say, the force magnitude is equal to kx. Leave that alone. K, again, is the spring constant. So this thing gets, let me draw another one here. It gets pulled this direction, right? That's the force being applied by the spring. And it gets pulled over to here. We're going to have some final velocity to look at here when it completely compresses, and we're going to know the distance that it traveled, right? So we're going to know this is our x naught, and let's just say, and this will be our x final. So we'll know the distance traveled. So the x is x final minus x initial. Okay. Now, this was a little different, right? So here we actually want to think about the integral, because we are integrating from x naught to x final of our force dx, but our force is actually a function of x. So this is going to be integrating from x initial to x final of kx dx, right? Now if I just go ahead and do this, generally speaking, my integral of kx is going to be 1/2 kx squared, right? Using my reverse power rule there. It's going to be evaluated from x naught to x final. So really this is just 1/2 k times x final squared minus x initial squared. All right, well, you can see here that this is really just this 1/2 kx squared, that's just the potential energy of a spring, right? So basically just used work energy theorem to show that when you're pulling on a block with a spring, you end up actually getting the potential energy stored in the spring. Lo and behold. The other way to look at this is we're actually going to have a graph, and I think what we actually do in this lab is you use the graph instead. You're going to have a force applied over a distance, and this thing is a linear force. It's equal to negative kx, right? So F equaling kx, it's kind of like y equals mx plus b, but b is 0 here, right? So it kind of looks linear, right? And that's the idea, is that it is linear. This thing is linear. So if you remember y equals mx plus b, you remember the m is your slope. Well, if you look at how that's analogous to our f equals kx, f is our vertical axis, x is our horizontal axis, so those are in the right position to make x and y. So the k must be our slope, right? Just by inspection, okay? And you'll notice that slope is your change in y over change in x. Change in y is, in this case, force. Change in x is position, so you get newtons over meter, which is what you expect for k. K has got to be newtons per meter. You can also see that k has got to be newtons per meter. How do I know that? Well, you can see right here, F is equal to kx. Okay, you plug a position, you plug like a meterage in there for x, right? And it should multiply k and give you a force. Well, k's got to be newtons over meters, so that if you multiply it by meters, meters cancel, you know the force. So yes, k has to be newtons per meter. Now, the way you're going to do this is, if using the graph, is that you would just calculate the area of this triangle here. So this is delta x, so your distance traveled right here. It's your base. Your maximum force would be here. And yeah, so we would just go ahead and find that work would be 1/2 your delta x times your height, which is your max force. In this case would be your, actually in this case it would be your k times delta x again. So actually I'll redefine this because it makes it a little better if I define this as actually not delta x, but this is 0, right? And this is my x final. So my work done would be 1/2 base times height, which in this case is 1/2 times x final times that force at x final, which is going to be k times x final. Okay, so then again, it just becomes 1/2 k times my x final squared. And you can see here actually that my x naught is equal to 0. So when I did this formulation up here, this thing goes to 0 and it's really just 1/2 k x final squared again. So that's because I started at position 0, which is going to be, you know, where it starts from. But anyway, okay. So that's the idea. In the lab, they just ask you to see if I can just pull it up really quick. Okay, in the lab here. Here's all your data, right? You don't really have to calculate anything. It's all right there. Well, the thing that you have to calculate is the energy and compare them, right? So for part A here, you have the masses of everything. You have the plus 4 stack of masses, actually. I forgot to mention that. Let's see. Yeah, you put the 4 masses on top of the cart, see? So when you're talking about mass of the cart, it's the cart itself plus the 4 stackable masses on top of it. Okay. There's your hanging mass, and there's your displacement. The area under the curve, that's basically the energy, right? What I was saying, the area under the curve is your energy because it's your work done. So what you're doing here is for part A is use your area measurement in table A2 to find the work done. Well, the area is the work done based on our discussion. Okay, so you just literally just write that there. What do you think would happen if the car is being pulled on both sides by equal masses? You can tell me after you figure that one out. Calculate the work done in the smart cart by a pulley system using the equation derived in the theory section. So that's the big nasty one. That's up here somewhere. I think they have it in here too. Yeah, right here. So this one, which was the tension times delta x, the tension that we calculated right there. That's the one that I want you to use for the second part of part A here. So calculate the work done. Yes, there it is. Calculate the percent error of the work value you found in question 1 compared to the value predicted by the theory, which you found in question 3. So basically, they're having you compare the one you calculated versus this area value, or this area value right up here, right? Then it says calculate your final kinetic energy, and then do another comparison. Okay, it's funny. Yeah, so here it is. Okay, so do this is using the final velocity. You do the 1/2 mv squared to find your kinetic energy at the end, which should be equal to this value, which was the work done. It should be equal to the calculated work done as well, right? Okay, and then linear force, same deal. So this one asks you, given the fact that the force in the spring is linear proportional to the displacement of the spring, which of the measured values in table B2 represents the spring constant? So you look up at table B2 here, and the thing that I was saying, this is basically your graph, right? This is your area under the curve. This is your average, which is not even important anymore. I don't know why they still have it in there. There's your slope. Hey, there's the slope, right? Your slope is the slope of your force versus distance graph for the spring is your K value, right? Because it looks linear. It's F equals KX, just kind of like Y equals MX, right? And M is your slope. Well, this time K is your slope. Okay, calculate the work done on the smart cart by a spring using the equation derived in the theory section. So that's the 1/2 kx squared thing that we talked about. And you can look at the top here. They gave it to you anyway. So you look at your displacement, you look at your K value, and you square your displacement, multiply by K, and divide by 2, and that's your value right here for number 3. Do the percent area for the area under the curve from table B2. So that's, compare this one right here, this value you got here, to the area value, which they give you up here. It's a little disjointed because they didn't have you write the area one down this time, but they mean for you to use it. So here it is. This area under the curve, again, is the work done, which should be the final energy, right? So they're having you calculate the final energy several different ways and then compare them is really what the gist of this lab is, right? So, okay, what is the slope, or what is the K value? It's the slope. What is the slope? What is the K value? Write it down. Calculate the work done. Compare it to that area under the curve thing. Use the final energy to calculate the total energy at the end. Final velocity to calculate your total energy at the end. And then do another comparison. And then answer this question right here, which is, let's see, it says show that the base SI units for work and energy are the same. Okay, well, I guess I can show you that one really quick. What they want you to do they basically want you to show that, so that the units of kinetic energy, which are joules, they want you to show that that's the same as work, which is newtons times meters. Well, so the thing is, the way I always think about joules, a joule is a newton times a meter, so there you go, that's done, right? But they kind of want you to, I guess, use kinetic energy itself to get from kinetic energy to work to joules. So we know that kinetic energy is joules. We know that kinetic energy is 1/2 mass times velocity squared, right? So basically they're saying that this kilogram times a meter over second quantity squared is also a joule. So how the heck is that the same as a Newton meter, right? And that's something we can show. So remember that your force is equal to mass of acceleration. So that's kilograms times meters per second squared, right? So if you take work, we can start at work here. Well, I can start either one. I'll start with this one over here. So we have kilograms, we have meters squared over second squared. What I can do is I can take one of those meters out of the top. So I just make this meters over second squared times meters, right? Which is just like unsimplifying it, it's factoring it out. And this piece right here, you can see is a Newton, right? Because a kilogram times a meter per second squared. That's a force, no, that's a mass of acceleration. So right there we have newtons times meters, which is work. Okay, so that's all they really want you to show. You can do the same thing with work up here. You can start with work and you can say, well, Newton is a kilogram times a meter per second squared, and then you have the other meter. So you have newtons is this part, and then times meters right here. And then, I can just multiply the top by meters and I get kilograms times meters over seconds quantity squared, which is like mass times velocity squared, and that's a joule. So basically what we've shown is that a joule is equal to a force times a distance. They're the same units. Okay. So all that being said, let's split you off into groups because that is, so awesome.